Good morning to all. Let us start the lesson Dual Nature of Matter. Today, in this lecture, I am going to cover the topics photon and its properties, photoelectric effect, experimental setup to study photoelectric effect, effect of intensity, frequency, potential on photoelectric current, graphical representation of variation of photoelectric current and laws of photoelectric effect. So let us start. Now photon. As you know that photon means a packet or bundle of energy. So bundle of energy or the packet of energy it called photon, and energy of photon is given by relation E is equal to h nu, where nu is the frequency of the photon, or E is equal to hc upon lambda, where h is the Planck's constant, nu is the frequency of radiation or photon, c is the speed of light, that is electromagnetic wave, and lambda is the wavelength. Now properties of photons. A photon travels at a speed of light c in vacuum, that is 3 into 10 raised to power 8 meter per second. It has zero rest mass, that is photon cannot exist at rest. The kinetic mass of a photon is m is equal to E upon c square is equal to h upon c lambda, because from the Einstein equation we know that E is equal to mc square. So same we can find out the mass of the photon is E upon c square is equal to h upon c lambda. The momentum of photon is P is equal to E upon c is equal to h upon lambda. Photon travels in a straight line. Energy of a photon depends upon frequency of the photon, because E is equal to h nu. So the energy of the photon does not change when photon travels from one medium to another. As we know that when light travels from one medium to another, its frequency does not change, and energy of the photon is directly proportional to the frequency. So the energy does not change when photon travels from one medium to another. But the wavelength of the photon changes in different media, and we can say the velocity of the photon is different in different media. Photons are electrically neutral. Photons may show diffraction under given conditions. Photons are not deviated by magnetic and electric fields. Photons are not deviated by magnetic and electric fields. That is why photons can emit the electrons from the surfaces of the metal. And this was proved by this is known as the photoelectric effect, and experimentally it has also proven. So let us discuss the photoelectric effect. Now we know, or you have studied in chemistry also, that whenever a light falls on a surface of the metals, then electrons are ejected from the surface of the metals, and such effect is known as the photoelectric effect. So we can say that phenomena of emission of electrons from mainly metal surfaces exposed to light energy like X-rays, gamma rays, UV rays, visible light, and even infrared rays of suitable frequency is known as photoelectric effect. The electrons emitted by this effect are called photoelectrons. Photo means the light, so since these electrons are ejected because of the light, so that is why they are known as the photoelectrons. The current constituted by the photoelectrons is known as the photoelectric current, and the effect is known as the photoelectric effect. Now photoelectric effect is not only shown by the metals. No, some of the non-metals also show photoelectric effect. Though we know that non-metals, they have a more affinity to electrons. There are no free electrons in the outermost surface, but still if the photons having such a high energies they can eject the electrons from their outermost orbit. Liquid and gases also show this effect, but to very limited extent. So metals, when the UV rays falls on the metal, photoelectrons are ejected. But when visible light falls on metals other than alkali metal, note to the point that when the visible light falls on metals which are not alkali, then no photoelectrons are seen. Only when visible light falls on alkali metal, then the photoelectrons are ejected. Now, experimental setup to study photoelectric effect. Now, this is a glass tube, C cathode, A anode, connected like this. This is the circuit diagram where C is the metallic cathode, A is metallic anode, and W is quartz window. Now, when the UV light through the quartz window falls on the metallic cathode, electrons are ejected and they are collected by the anode. Glass transmits only visible and infrared lights but not UV light. That is why the window is made up of the quartz, so that the UV light may travel or pass through this window. Now, when light of suitable frequency falls on the metallic cathode, photoelectrons are emitted. These photoelectrons are attracted towards the positive anode and hence photoelectric current is constituted. Now let us discuss the result of the photoelectric experiment or the observations done or seen during the photoelectric experiment. Now, effect of intensity of incident light on photoelectric current. Now, it was observed that when we draw a graph between intensity and the photoelectric current, it is a straight line. That means that intensity of the light is photoelectric current is directly proportional to the intensity of light. So, for a fixed frequency, the photoelectric current increases linearly with increase in intensity of incident light. This was observed during the experiment. Then another experiment result, that the effect of potential on photoelectric current. Now this is the potential of the anode photoelectric current. Now it is observed that L1 is the intensity of the light. When the potential is increased, then photocurrent increases. The photocurrent increases, and after that it reaches to a saturation value. So this is the saturation current. If L2, that is the intensity, is increased, then amount of the photocurrent increases, and then again it reaches to the saturation current. So L2 is greater than L1. Saturation current is more for the higher intensity of radiation. So for a fixed frequency and intensity of incident light, the photoelectric current increases with increase in positive potential and to the anode. When all the photoelectrons reach the plate A, current becomes maximum and is known as saturation current. Now, if we reduce the anode potential towards the negative direction, then the photocurrent starts decreasing. But for the zero potential, the photocurrent does not become zero, it has some value. So, when the potential of the anode is decreased and taken to the negative value, then at zero potential, the photocurrent does not become negative, and when the potential is decreased, the current decreases but does not become zero at zero potential. This shows that even in the absence of accelerating potential, few photoelectrons manage to reach the plate on their own due to their kinetic energy. So listen once again, even the potential of the anode is zero, but still there is a photocurrent because some of the photoelectrons, they have a kinetic energy of their own due to which they reach to the anode and constitute the photoelectric current. When negative potential is applied to the plate A with respect to C, photoelectric current becomes zero. at a particular value of negative potential called stopping potential or the cutoff potential. So when this potential is increased to the negative potential, then at particular value of the potential the photocurrent becomes zero. This potential is known as the stopping potential or known as the cutoff potential. Cutoff potential because at this value the photocurrent is totally cut off or photocurrent has become zero. So intensity of the incident light does not affect the stopping potential. This also observed during the experiment that L1, L2. These are the two graphs. When L2 is more than L1, the saturation current is amount of the photocurrent is increased, but the amount of the stopping potential, the value of the stopping potential remains same, and it does not depend upon the intensity of the light. Now, effect of frequency of incident light on photoelectric current. Now, in this here, when intensity is increased, then photocurrent is increased. Now, when frequency of the light photon is increased, means its energy is increased, even it is noticed that the photocurrent does not increases, means by increasing the intensity of frequency of incident light, the photocurrent does not increases. For a fixed intensity of incident light, the photoelectric current does not depend upon the frequency of the incident light, because the photoelectric current simply depends upon the number of photoelectrons emitted, and in turn on the number of photons incident and not on the energy of photon. Now it was observed and the conclusion drawn that one photon can eject only one electron. Whatever be its frequency should be greater than particular limit, and if it has a certain frequency, certain energy, then it can eject the electron. One photon can eject only one electron. So that is why as we increase the intensity, increasing intensity means we are increasing the number of photons. Number of photons are increasing means number of photoelectrons, ejected electrons increased and photocurrent increased. But if we increase the frequency means we are not increasing the number of photons. We are increasing only its energy h nu. So as the number of photons are not increased by increasing the frequency, so photocurrent does not do not increase. Effect of frequency of incident light on stopping potential. So let us observe this. Now this is the potential of anode, the current. Now for the particular intensity of light, there is a stopping potential S1. Now if for the same photons, for the same intensity, energy is increased, means the frequency is increased, it is observed that the stopping potential is increased. For a fixed intensity of incident light, the photoelectric current increases and its saturated value with increase in positive potential applies to the anode. However, the saturation current is same for different frequencies of the incident light. When potential is decreased and taken below zero, photoelectric current decreases to zero, but at different stopping potentials for different frequencies. So it is observed if the intensity is increased, then saturation current is increased, but for the same saturation intensity, if frequency is increased, then stopping potential increases. Higher the frequency, higher the stopping potential. Threshold frequency or the cutoff frequency. It is observed that if we draw a graph between the stopping potential and anode potential and the frequency, so the graph between stopping potential and the frequency does not pass through the origin. It shows that there is a minimum value of the frequency called threshold frequency, below which photoelectric emission is not possible. however high the intensity of incident light may be. It depends upon the nature of the metal emitting electrons. So it was observed that for a particular metal there is a cutoff frequency below which if the photon has energy, then photoelectron cannot be emitted. Means certain energy is required for a particular metal to eject its electrons. So such frequency is known as threshold frequency. Value of threshold frequency is different for the different metals. It depends upon the work function of the metal. Work function means the minimum energy required to eject the electrons. So this value is different for the different metals, and as a result the cutoff frequency or the threshold frequency is different for the different metals. On the basis of these observations, law of photoelectric emission has been designed. These are: for a given substance there is a minimum value of the frequency of incident light called threshold frequency, below which no photoelectric emission is possible, however the intensity of incident light may be. That means that intensity of the incident light may be whatever may be, means whatever number of photons may fall on the metal, but if the energy of each photon is not up to the above the threshold frequency, it will not eject the photoelectrons. The number of photoelectrons emitted per second, that is the photoelectric current, is directly proportional to the intensity of incident light, provided the frequency is above the threshold frequency. So if the frequency of the photon is above the threshold frequency, then the amount of the current depends upon the intensity of light, that means the number of photons, because one photon can eject only one photoelectron provided its energy frequency is above the threshold frequency. The minimum kinetic energy of the photoelectrons is directly proportional to the frequency provided the frequency is above the threshold frequency. So now energy of the photon, whatever is the energy of the photon, part of energy is used to eject the electron and the rest of the energy is provided to the electron as its kinetic energy. So if more the energy of the photon, more will be the kinetic energy, because the work function is fixed for a particular metal. So part of the energy is used to eject the electron from the surface of the metal, and the rest of it will be transferred to the to increase its kinetic energy. So we can say that kinetic energy is directly proportional to the frequency. The maximum kinetic energy of the photoelectrons is independent of the intensity of the incident light. The process of photoelectric emission is instantaneous. That is, as soon as the photon of suitable frequency falls on the substance, it emits photoelectrons. It does not take any time. It is a spontaneous process. The photoelectric emission is 1:1. That is, for every photon of suitable frequency, one electron is emitted. So these are the laws of photoelectric emission, which was framed on the basis of the photoelectric experiments. So that is all for today's lecture. Thank you and have a nice day.